Good afternoon, everyone. Welcome. Remember to turn on your cameras if you don't mind, so I can see you and get your feedback. And it helps me just to continue to feel like I'm, lecturing to people instead of just microphone. So that would help me a lot. Thanks. Let's see. We finished chapter 8. We have one more chapter to go before the exam. That's chapter 9 on periodic properties. So we'll be starting that today. Next week, we have class on Monday, and then Wednesday is a holiday, and then the exam will be on the following Monday, November 16th. Okay? So that's where we're at. Any questions before we get going?
Does that mean that we don't have lab next week either?
Right. There's no lab next week. Correct. Any other questions before we get going? Okay. Let's go ahead and start. So I want to remind you of a law that we learned about earlier called the periodic law, and it was presented by Mendeleev, Dmitry Mendeleev, who was a Russian chemistry professor. It was in 1869, and at the time, people had discovered about 50 or 60 elements, right? And they began to observe some of their properties, and they began to know more and more about these elements, but there was no real systematic way to organize them. And so Mendeleev looked at those properties, at the properties that resulted from observations, right? And he formed a law. Remember how science works, right? Observations lead to laws, and then both those together can lead to theories or models, right? So the observations were the properties of these elements, and then Mendeleev formed the periodic law as a way to summarize those properties. And he said when elements are arranged in order of increasing atomic mass, certain properties recur periodically, okay? And then, according to the scientific approach to knowledge, right, we move from observation and laws to theories or models. The model that explains this law and much, much more is the quantum mechanical model, which we just finished learning about, right? So we're going to tie all this together and show how the model explains this law, right? And also how it explains the arrangement of the entire periodic table, all right? So let's go back to Mendeleev for a minute. Actually, let me talk for a minute about what I mean by periodic properties, because this chapter is about periodic properties. So periodic properties are, you can see a periodic property here. If you look at the column in the periodic table that begins with boron, right? Boron, aluminum, gallium, and indium, and you plot some of the properties of those elements, you see a trend, right? It's not necessarily a smooth trend, but you see that the radius increases generally, right, as you go down, and you see that the density increases as you go down, okay? So this is a periodic trend, all right? And radius and density would be periodic properties. And so, of course, what we're interested in this class ultimately, right, is tying together structure and properties, right? So these are some properties, and we want to be able to tie that to structure. And what I mean by structure for elements is the structure of the electrons in the atom, right? Structure determines properties. So we want to understand how the arrangement of electrons in atoms, their structure, determines properties like these, all right? And we'll see that quantum mechanics brings that together for us, and it also explains why we have these periodic properties, okay? All right, so the periodic law, we can imagine it sort of in a picture like this, all right? If we list the elements, right, in order of increasing atomic mass, and we just let a color represent one of its properties, one of that element's properties, we see a pattern, right? We see a pattern. And the pattern is that you see in this case, this kind of salmon color, green, blue, purple. Again, this represents some property. It doesn't matter what the property is. And then you go along and you see that same pattern repeat itself. Salmon, green, blue, purple, salmon, green, blue, purple, right? So this is the pattern that Mendeleev saw in 1869, all right? This pattern of recurring properties in this sort of regular pattern, all right? And so he said, well, what happens if we then just move these elements, instead of listing them like this, just move them to form a table so that elements with the same properties line up in columns, right? That's what he did. And that was the first, this isn't exactly it, but Mendeleev was able to put together the first periodic table using this idea. Now, remember, he had no reason why this happened, right? That didn't come till much later. Quantum mechanics explains why, right? Quantum mechanics is the model that explains why. The periodic table really is just a result or an expression of the periodic law, okay? And that's what Mendeleev did. Mendeleev, amazingly, one of the things that was remarkable about his arrangement was that his table had certain gaps in it. So when he arranged his table, he saw, oh, there's a gap here, there's a gap here. And he thought, okay, those must be elements that have not yet been discovered. Because remember, in 1869, not all elements had been discovered. Only about 50 or 60 of them had been discovered. So he had some gaps in his table. So he predicted the existence of these elements. For example, gallium, which what we call gallium now, which he called Ica aluminum, which would fall right here, right? And germanium, which he called Ica silicon, which would fall right here. And not only did he predict the existence of these, but by looking at the properties of the elements that were around them in the periodic table, he was able to predict some of their properties. So for example, he predicted the atomic mass, he predicted the melting point, he predicted the density, he predicted how they would react with other elements to form compounds with certain formulas, right? And look at that. When they actually discovered those elements, Mendeleev was right on, right? Ica means the one after, I think. I think it means the one after. So Ica aluminum is the one after aluminum, and Ica silicon is the one. I think that's what it means. I'm not 100% sure, but I think that's what it means. And germanium, same story, right? He said, oh, look, here's what I think its properties should be. And sure enough, he was right. So he kind of impressed the scientific world with those predictions and with his periodic table, okay? And of course, that involved in the periodic table that we all know and love and have been using already for most of this semester. But what we want to do is be able to now connect that periodic table and the way it's arranged to the model which explains why the periodic table is as it is, okay? And that model is the quantum mechanical model, which we have already been looking at. All right, so the key to that connection is to know where the electrons are, right? Because it's the electron structure, what kinds of orbitals the electrons are in, that end up giving the element its properties, all right? So last time we had talked about electron configurations, where we have the name of an orbital like this. So for hydrogen, this would indicate the 1s orbital, and this would be the number of electrons in that orbital, right? So the electron configuration for hydrogen is 1s1, right? Which means it has one electron in the 1s orbital.
I have a question.
Sure.
So since Mendeleev knew that there were ones that hadn't been discovered yet, does that mean there are still some that haven't been discovered, or?
Good question. So if you look at the periodic table today, it looks pretty full. There are no gaps, right?
Oh yeah.
But what we have been discovering even recently is elements that are synthetic. That means you can make them, and you can make them by basically by nuclear processes, by smashing together atoms or smashing neutrons into atoms and having those neutrons incorporated into the nucleus and then build bigger and bigger atoms. So we have been, and if you look at the very bottom row of the periodic table in your book, let's see, you'll see, do I have one here? Yeah, like these elements, and actually these recently have been named as well, but these really heavy elements have recently been synthesized. Now, these elements are, it turns out, are not very stable. All right, the nucleus is not very stable. So a lot of times they'll be made in some of these atom smashers, and they'll only stay together for a small fraction of a second, and then they'll fall apart. All right, but you can see the rest of the periodic table is pretty filled up. So the only place for discovery of new elements would be here in the heavier element range. And like I said, we have discovered some of those. And in fact, everything above lead on the periodic table, everything above bismuth in the periodic table is actually energetically unstable and will actually fall apart over time, because once atoms get too big, their nuclei just don't hold together anymore. So we'll learn more about that next semester when we look at nuclear processes. Okay, but great question. Okay. Then we can also, as we saw last time as well, write an orbital diagram, in which case a box represents the orbital and a little half arrow represents the electron. When it's pointing up like this, that means that the spin quantum number is +1/2. If it points down, that means the spin quantum number is -1/2, right? So I think that's where we were at the end of last time. Now we want to be able to write electron configurations and orbital diagrams like this for more elements besides just hydrogen. All right. So in order to do that, in other words, in order to know where the electrons are in elements other than hydrogen, we need a couple more concepts. All right. One of them is the Pauli exclusion principle. And the Pauli exclusion principle states that no two electrons can have the same 4 quantum numbers, right? So if you think about helium that has 2 electrons, the second electron, if it's going to go to this lowest energy 1s orbital, right, has got to have a spin quantum number of -1/2, all right? So when we put 2 electrons in an orbital, they got to be spin paired. The Pauli exclusion principle also implies that you can't have any more than 2 electrons in a single orbital, right? Because if I added a third one into here, it would have to be either spin up or spin down, and then it would have the same 4 quantum numbers as one of these other ones, okay? So the Pauli exclusion principle limits the number of electrons that we can put in an orbital to 2. The second thing we got to understand is a concept called sublevel splitting. So for the hydrogen atom, we know that only the principal quantum number determines the energy of the orbital, right? So n = 1 has some energy, n = 2 has some energy, n = 3 has some energy, right? And we know that equation, -2.178 times 10 to the -18 joules over n squared, right? So we can find the energy for any one of these orbitals. But in a given value of n, right, you have a lot of orbitals with the same energy in the hydrogen atom, right? We say that these are degenerate orbitals. They have the same energy. So all of these have the same energy, all of these, and so on, right? In multi-electron atoms, once we get to beyond helium, the energy ordering is no longer degenerate for a given value of n. All right, so you can see here that the 2s orbital has less energy than the 2p orbital, even though the value of n is the same. So that equation that I gave you earlier for the energy of an orbital based on n is only for the hydrogen atom, okay? For all other atoms, the energy, that degeneracy breaks up according to sublevel. So the s sublevel is lower than the p sublevel, and the P sublevel is lower than lower than the D sublevel, sorry, and so on. All right. So we want to be able to understand this a little bit. And in order to understand this, which ends up determining, right, how electrons fill these levels, we need to understand, first of all, Coulomb's law. And I mentioned Coulomb's law briefly before, but basically Coulomb's law gives us the potential energy of two charged particles, okay? So the potential energy of two charged particles, of two charged particles, that energy is equal to, let me see, 4 pi, 1 over 4 pi epsilon 0. This is just a constant with a value of 8.85 times 10 to the minus 12 Coulomb squared joules meters, all right, times Q1, Q2. These are the charges of the particles. And we divide by R, that's the separation or the distance between the particles. So if you have particle Q1, Q2, their potential energy depends on two things: how big the charges are and the distance between them. And of course, the sign of the charges, okay? So a couple of things to realize. One, if the charges are small, let's see. First of all, if the charges have the same sign, right, then Q1 and Q2 are both positive. So that means that the energy of interaction is also positive, right? When these two particles interact, it's going to raise their potential energy, right? So if the potential energy gets higher as they come closer together, right, because it's 1 over R, right? As R gets smaller, potential energy gets bigger, right? So their potential energy goes up as they come together, which means that they what each other?
Attract.
Not with the same charge. If they both have the same charge and this is positive, which, right, because positive, positive, this is all positive. As they come together, their potential energy goes up, right? So things tend to go to lower potential energy. So as they try to come together, what do? Attract or repel?
They repel.
They repel, right? Because as you come closer, their potential energy goes up. It's like forcing together two north poles of a magnet, right? When you force them together, they repel each other, okay? If Q1 and Q2 are opposite in sign, though, then as they get closer together, the potential energy is more and more negative, right? Becomes more and more negative. So that means if it becomes more and more negative, that means that they attract each other, kind of like opposite poles of a magnet would. All right. So that the magnitude of that attraction and repulsion depends on two things: the product of the two charges. The bigger the charge is, the more the attraction or the more the repulsion. Yeah. And it depends inversely on the distance between them. The closer they are, the stronger the attraction or the stronger the repulsion. Are you with me? Awesome. Okay. So now we can understand why, now we can begin to understand why this happens, why we get this sublevel, what's called sublevel splitting. We call it sublevel splitting because the sublevels here are degenerate, but here they're split up, so they no longer have the same energy. All right. So we want to imagine the lithium atom, which is right. Lithium is right here, right? It has. Are you with me? Can you hear me? Okay, lithium is right here. It has 3 protons and 3 electrons, right? So, so its nucleus is 3 plus. The first 2 electrons are in the 1s orbital, all right? And then I want to ask a question about this third electron to help us understand shielding and penetration. We can think of the repulsions. Now remember, this electron is feeling 2 things, right? It's feeling the attraction of the positive nucleus, right? Because that's a positive negative interaction, which according to Coulomb's law is an attraction, right? But it's also feeling the repulsion from these 2 electrons, right? So it feels the 3 plus pull of the nucleus and the minus of the electrons. So we can think of the repulsions of the electrons as what we call shielding, all right? In other words, this electron, if you can imagine, when it looks in, it sees this 3 plus nucleus through a cloud of 2 minus, right? So it experiences an effective nuclear charge that is maybe about what?
+1.
Plus 1. Yeah, exactly right. It experiences an effective nuclear charge of about +1 when it's out here. All right. Now, penetration is when an electron can penetrate or go into a core electron cloud. All right. If we move this electron from here to there, the nuclear charge that it experiences out here is 2 plus. But once it gets close to this nucleus, what do you think happens to the charge it experiences?
It increases.
It increases. Exactly right. It increases. And since this is a plus and minus, right? According to Coulomb's law, what happens to its energy, right? As the charge goes up?
It become more negative.
Become more negative. Exactly right. Very, very good. It becomes more negative. So its energy would go down, right? It would become more stable, right? Its energy would go down. Does everyone understand that? 2 key concepts. Shielding, that is, that core electrons can shield or block outer electrons from nuclear charge. Secondly, penetration, electrons that can penetrate close to the nucleus into the region occupied by core electrons have a lower potential energy. Okay? Those are the 2 main ideas. And if you can understand those ideas, then you can understand why this happens. All right? So let's go back and look at the total radial probability for the 2s and the 2p electrons. Remember what this is. This is the plot of the total chance an electron will be found in a thin spherical shell at a radius r from the nucleus. All right, remember these plots from before, from the last chapter? The 2s and the 2p. Now, here's what we're trying to explain. We're trying to explain why, in the case of hydrogen, 2s and 2p all have the same energy. But in the case of multi-electron atoms, 2s and 2p have different energies, with the 2s orbital being lower in energy than the 2p, right? That's what we're trying to explain. So look what happens. If here is the total radial probability of the 2s orbital, and here it is for 2p. All right. If there are no electrons in the 1s orbital, in other words, if the 1s orbital is empty, and here's the total radial probability for the 1s orbital, right? If there are no electrons in the 1s orbital, then the 2s and the 2p orbitals have exactly the same energy. They're degenerate, okay, like we said earlier. All right. However, if this is occupied by electrons, if the 1s orbital has electrons in it, like it would in a multi-electron atom, okay, then look what happens. These electrons shield these electrons from the nuclear charge, right? because they're the core electrons that are close to the nucleus. In other words, these electrons here in the 1s orbital are basically these electrons here. Yeah. If an electron is in the 2p orbital, it spends most of its time in this. This is its probability, right? It spends its time at these distances. If it's in the 2s orbital, it spends its time here. But notice the difference. The 2s orbital has this little bump right here, which significantly penetrates into the core 1s electron cloud, right? So the 2s electrons can basically do this, or at least spend some of their time in that cloud. When they do that, when they're found in that area, they overall have a lower energy, right? For the reasons we just said, they experience higher nuclear charge. So because of that, the 2s orbital is lower in energy than the 2p orbital when there are electrons in the 1s orbital, right? So for all multi-electron atoms, the 2s and the 2p orbitals are no longer degenerate. Why? Because the 2s orbital penetrates into the core region, right? And we can see that penetration right here, this little bump of probability that's very, very close to the nucleus. Okay? I see a question from Taylor.
Is that what makes the orbital shapes?
No, remember that the shape of the 2s orbital is spherical and the shape of the 2p orbital is like a dumbbell, right?
But like, since S1 or 1s is just a ball and then S2 is just a bigger
Yes.
ball, basically, is that what makes it able to have penetration? And
It's this little, it's this, remember that the 2s is like the 1s except that it has a node, right?
and
There's the node,
Yeah.
and then it has this region of probability that's very close to the nucleus. That's what penetration is,
okay.
right? So there's a probable chance of finding the electron there within this core, which means that there's a probability of finding the electron in this position. And in that position, it has a lower energy, right, than it would out here.
Okay.
Okay. So that's what penetration is, right? It's this little bump that we find close to that core. If we now look at the 3s, 3p, and 3d, we see a similar thing. The 3s has this little bump and this little bump, right? Look at that, penetration of the 3s orbital into the core electron region. Similarly, the 3p has a node and then penetration, right? The 3d doesn't have that same thing, right? So therefore, the 3s, because of that, is lower in energy than the 3p. The 3p, because of this, is lower in energy than the 3d. All right? So then we get this energy distribution, okay? Where now for a principal quantum number, you no longer have all the same energies. Why? Because the 2s penetrates more than the 2p and therefore has lower energy. The 3s penetrates more than the 3p, therefore has lower energy. The 3p penetrates more than the 3d and therefore has lower energy. All right, so we see this splitting of energies. Megan.
Do you mind repeating what you said regarding if there are electrons found in the 1s orbitals? Is that when
Yes.
shielding occurs?
Right. If there are no, imagine this, let's go back to this for a minute. If these electrons weren't here, right, these two electrons, there would be no shielding. And then penetration wouldn't matter. All right. So that's what you have in the hydrogen atom, right? You only have one electron. So if the electron is up here or here or here, there are no core electrons present that would shield it from nuclear charge because there's only one electron, right? So that's why this phenomenon of the splitting of the sublevels applies only to multi-electron atoms, right? It doesn't apply to hydrogen. So when we go from hydrogen to these multi-electron atoms, you get this change in the energies of the sublevels. Does that answer your question? Great. Let's see, Michael.
Hey, I just had a question in regards to interpreting these graphs. So you're saying where that bump occurs in the s orbital, yeah, like in that 1s orbital, but you also, relatively speaking, still have a high probability of finding electrons in the 2p breaking through?
Correct. So there is a little bit of penetration here from the 2p, but it's not as significant as this because this penetrates much further into the core than that does.
Okay.
And it's that getting the closer you get, the higher that Q becomes,
Yeah.
right? When you get really close, the effective nuclear charge is 3+, right? But even here, you still feel the repulsion of the other electrons a little bit more. So there's still more shielding, right? So it's the fact that you have some probability density of finding the electron here, as well as how close that is to the nucleus and how much it penetrates the 1s that results in the energy lowering of that orbital.
Yeah. Okay. Thank you.
Yeah, absolutely. Nayeli.
So would you say that like in terms of the energy levels, the orbital that doesn't have any penetration, would you say that that's the highest energy level?
Correct. Exactly right. Exactly right. When the electron is out here, it's feeling the smallest amount of effective nuclear charge. And since that's smallest, that would have the highest potential energy. Sorry. It would have, yeah, the highest potential energy, right? Because this is plus minus interaction.
And would you say like if it has like, if there's like more bumps in the graph, would you say that that's a lower energy level kind of?
If the bumps penetrate into the core region. So in other words, the electron has to get into this region, has to have some probability of being found in this core region in order for its energy to be decreased, right? Because then it experiences a higher charge. So you can see here's the core region, and you see how this penetrates into that. That's what causes its energy to go down.
Okay, got it.
Because it really experiences that full 3+ charge of the nucleus, and that lowers its potential energy. Okay, so let's see if we're getting this. Try to answer this question. Let me give you a little hint. If an electron penetrates into this region, it feels the nuclear attraction more strongly, correct? And when it has that stronger attraction to that nucleus, right, does its energy goes down, right? It has lower potential energy. Why? Because the plus and minus are opposite in charge, right? So when you look at Coulomb's law, Q1 and Q2 are opposite in charge, which means that this energy is negative, right? So as R gets smaller, as those two numbers get bigger, that product gets bigger. The energy gets smaller, right? So it gets lower. So again, as the electron penetrates into this cloud, its energy gets lower. Its potential energy gets lower, right? That's why the 2s orbital is lower in energy than the 2p, because the 2s penetrates more than the 2p. All right, try that again. Or I guess you can't. I guess you can't re-vote, huh? I'm gonna start it over. Let's try it again. See, I really love these polls because I can correct. I can see what you guys are thinking and I can correct that, right? So this is why I love it when you do these polls for me. It informs me, it helps you to learn, and it helps me to know how well you're understanding something. All right, try to choose an answer the next 10 seconds or so. Okay, the right answer is C, which most of you got now. Let's see, a couple of you put D, a few of you put D. An orbital that penetrates the occupied core is more shielded from nuclear charge. Okay, let's think about that. It says an orbital that penetrates into the region occupied by a core electron is more shielded from nuclear charge. What happens to this electron as it penetrates into the core region? Does it see more shielding from nuclear charge or less shielding from nuclear charge?
Less.
Less, right? It sees less shielding. Out here, it sees the 3+ charge through this 2- cloud. But in here, it sees that 3+ charge directly, right? It's less shielded, and therefore it's lower energy. Okay. All right. Very good. I think we got that. Let's move on, because now that we know the general energy ordering, now we can tell where the electrons are going to go, because a couple of things are going to happen. One, first of all, the electrons in a particular atom are going to go to the lowest energy orbitals possible, right? Except remember that each orbital can only hold 2 electrons max, right? So if we keep that in mind, each orbital can hold a maximum of 2 electrons. Then we can start filling these up. So for example, if we were to write the electron configuration for lithium, right, which has 3 electrons, it'd be 1s2, 2s1, right? We'd put 2 electrons into here, and then that's full, so we put the next one into there, right? If we march our way across the periodic table, right, right after lithium, right, we can write the electron configuration for beryllium, right? Beryllium has 4 electrons, right? So we'd go 1, 2, and then 3, and where would the 4th one go?
2s.
Into the 2s, but it would just have to be spin paired, right? So 1s2, 2s2. And if we write the orbital diagrams here, they would look like this. This would be 1s, right? And this would be, sorry, 2s, 1, right? For this guy, it'd be like that, right? And then the next element would be boron. So it has 5 electrons, right? So we go 1, 2, 3, 4, and where would the 5th one go? 2p, exactly right. So we'd have 1s2, 2s2, 2p1, right? And if we drew the orbital diagram, it'd look like this, 2p1. All right. The next element on the periodic table is carbon, right? It has 6 electrons. So where would that, where would that, we'd have 1, 2, 3, 4, and then 2 would have to go into the 2p orbitals. Now the question is, do they both go in the same orbital, or do they occupy 2 separate ones, those 2 electrons?
Separate ones.
Separate ones, correct. And that is Hund's rule, okay? Hund's rule says when filling degenerate orbitals, remember what degenerate means?
Orbitals of the same,
Energy.
yeah. That's
Orbitals
it.
of the same energy, right? So when filling degenerate orbitals, fill them singly first with parallel spins, right? So we'd have, for carbon, we'd have 1s2, 2s2, 2p2, right? Which would look like this. This is the 2p orbital, right? And we put 1 here and 1 there. Okay, so we can just keep doing this. And if we keep doing this, right, we can write electron configurations for any element in the periodic table, right? Just by filling them up in this same order, right? So if we get to fluorine, it has 7 electrons, right? We go 1, 2, 2 here, 2 here, and then we go 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. It has 9 electrons. 5, 6, 7, 8, 9, and we get this orbital diagram.
Are we going to have to deal with configurations that go past 4D?
I want you to know about them, but I will not be asking you to write them.
Okay.
Okay, so keep this in mind, and keep this energy ordering in mind. I want to show you a kind of a shortcut way to write electron configurations in which you don't have to memorize this order, because notice this order is a little bit tricky. You have 1s, 2s, 2p, 3s, 3p, and then you might think you go to 3D, but look at that, 4s sneaks in before the 3D. All right, so the way of filling would be here, 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 and then here, and then there. Okay, but luckily we can tell electron configurations just from the position of an element in the periodic table. Okay, and you guys watched the video on this already too, right? Right. So okay, so I'm just going to introduce a couple concepts, and we'll just go through that together to review it. Let's see. In what case we use orbital F? When you have enough electrons, I'll show you all that in a minute. So the first thing we want to do, though, before we get to that, in order to understand the way the periodic table and the filling of orbitals corresponds to one another, let's define something called valence electrons. Okay. Valence electrons are the electrons that are important in chemical bonding. All right. And those are the ones we're most interested in. And turns out that the electrons that are most important in chemical bonding are the ones that are held most loosely, right? The electrons that are held really tightly don't get shared or transferred, all right? But the ones that are held most loosely are the ones that are more easily shared or transferred. So since chemical bonding is a sharing or transfer of electrons, it's the valence electrons that are most important in chemical bonding, all right? Nayeli?
Yeah, my question was kind of regarding the example that you did for carbon. So do you fill the spin number kind of like left to right on the 2p or?
Yeah, just by tradition, that's the way we do it. And tradition, we usually just put spin up first and then spin down when it's paired. But in reality, the important thing is that they all have the same spin. Whether it's spin up or spin down, we really can't tell. But just by convention, we usually write them spin up like this. They absolutely must have the same spin. Okay, according to Hund's rule.
Yeah, because I think I'm kind of confused as to why like that one wouldn't be paired on like the last one, and why it's like spin up and then another spin up.
Why wouldn't this one be right here?
Yeah.
So it turns out it's because of energy considerations. Okay, when you put two electrons into the same energy, when you put two electrons into the same orbital, that's higher in energy than if you put them in separate orbitals, right? Because they have electron-electron repulsions to deal with if they're in the same region of space. Because remember what an orbital represents is where the electron exists, right? And if you cram them in the same region of space, they repel each other more, and therefore they have higher energy. If they go into separate orbitals like this, they spread out more and they therefore have lower energy. So that's why.
Okay.
Okay? And that's what Hund's rule helps us to remember. Okay. All right, so the valence electrons, and then for main group elements, the valence electrons are those electrons in the outermost principal energy level. All right, those electrons in the outermost principal energy level. So for example, here for silicon, here's its electron configuration: 1s2, 2s2, 2p6, 3s2, 3p6. So where are the valence electrons? These are the valence electrons, right? Because you have n equal 1, n equal 2, n equal 3, right? N equal 3 is the highest principal energy level. How many electrons in the n equal 3 level? 2 in the s, 2 in the p, for a total of 4. So we say that silicon has 4 valence electrons. All right? Here is the entire periodic table showing the valence electrons for each element. All right? And the valence electrons, notice for the non-main group element, remember this is for main group elements, the concept of valence electrons is most important for main group elements. For these elements, which are called transition elements, we also include the d electrons as part of the valence electrons, even though they're not in the outermost n level, right? They're not in the highest principal energy level. But what I want you to notice here is how these things are filling, right? As you go from hydrogen to helium, you fill the 1s orbitals, right? And then you go to the second period in the periodic table, the second row, right? And then you fill 2s, and then you jump over here and you fill the 2p, right? So notice as you cross this way, you're always filling the s orbitals, right? As you cross this block, you're constantly filling the p orbitals. As you cross this block, you're filling the
d orbitals.
d orbitals, right? So this is called the s block, the p block, and the d block, right? As you go down any column, right, you have the same number of valence electrons. They're just in an orbital with higher n number, right? For the s and p blocks, the principal quantum number is just equal to the row number, right? So here 2s1, 2s2 is in row 2, right? 3s1, 3s2, row 3, 3p1, 3p2, row 3, right? Once you get to the d block, the d orbitals are being filled are equal to the period or the row number minus 1, right? So in this period, what are you filling? In period 4, you're filling the 3d. In period 5, you're filling the 4d, right? Period 6, you're filling the 5d. For the f orbitals, which are down here, the period that you're filling is sorry, the F orbital that you're filling is the period number -2, right? So these two come right out of this. This comes out of right out of here to just to make the periodic table easier to fit on a page, right? But that's period number 6, right? And notice you're filling the 4f orbitals as you cross here. Notice also that each of these blocks, its width is determined by how many electrons fit in those orbitals, right? So for the s block, it's 2 columns wide. Why? S orbital holds 2 electrons, right? For the p block, it's 6 columns wide. Why? Because the p orbitals hold how many electrons?
6.
6, right? The d block is 10 columns wide because the d orbitals hold 10 electrons because there's 5 of them, right? And so on. All right. All right. A couple of questions here. I see Nayeli. Oh, did you already get your question, Nayeli? Did you have another one?
I guess so. So you said that like in terms of like I don't know how to explain this question, but when you go into the D block,
Yeah.
or the D block, is it the
This block right here. The yellow
No.
one.
The P block
P block
is,
right here.
oh my God, wait, no. Yeah, I don't know how to explain it. I'm sorry.
Okay, no worries. Think about it, and then if you can articulate it, then ask me again. Abe.
Yeah, I was trying to figure out what exactly so like I was doing the homework yesterday and I was trying to figure out what like I think it was called like half shells for like chromium, like why exactly they have the 4s1.
Yeah,
and then
we'll get to that in a minute, okay?
Okay.
We'll get to that in a minute. Taylor.
Does your row number, like for instance, row 10, does that tell you how many valence electrons you have too?
The column number, that's labeled with A tells you how many valence electrons.
Okay.
Okay, so for example, for 5A column, notice there's 5 valence electrons, right? In every case. 6A, 6 valence electrons. So this number right here tells you the number of valence electrons.
Okay. Thank you.
The row number tells you the highest principal quantum level. Okay.
Okay.
All right, so that's really nice, right? Because now we can just write electron configurations by looking at the periodic table, right? So for example, what's the electron configuration for chlorine, right? So we just go, okay, here's chlorine. So what we can do is we trace backwards to the nearest noble gas. All right, so we trace backwards. Remember, the periodic table goes boom and then boom. So if we're tracing backwards, we go boom and then boom. We trace backward to the nearest noble gas. And we can use this core notation, which looks like this. This neon in brackets just symbolizes the electron configuration for neon. All right, so in other words, this stands for 1s2, 2s2, 2p6. All right. So we go back to that. We write that. And again, we're writing the electron configuration for chlorine. And then we just start tracing to the right across the periodic table. And we see, aha, we crossed the 3s. We crossed the s block for the 3rd period. So then we write 3s2. And then we go all the way over here and we can start in the 3p block, right? I mean, the p block in the 3rd period. So then we count 1, 2, 3, 4, 5. So the electron configuration for chlorine is just that. Are you with me? Let's see. For sodium is right here, right? So what do? We trace back to the nearest noble gas. That's easy. That's neon again. So this is for sodium, the electron configuration. It's neon, and then it's just what?
3s1.
3s1, right? Okay, what about tellurium? Te, which is number 52 right here. So we trace back to the nearest noble gas. That's the noble gas that sits here, right? Neon, argon, krypton, all right? So that's going to be a krypton core right here. And then we're going to go to the right. And we're going to go what? 5s 2. And then remember, this row of D is what? What's the principal quantum number for this row of D elements? Is it 5?
Oh.
4.
4, right? When you get to the D elements, it's always this number minus 1. It's always the row number minus 1, right? So we're going to write 4D, 4D.
The paper.
Yeah, 4D. And it's going to be 4D what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4D 10, right? Those are all full. And then we get to what? What are these?
The F block.
Not the F block.
Wait, sorry, P block.
P block. P block. And what's the principal quantum number there?
5.
5. So it's going to be 5p what? 1, 2, 3,
4.
4. See how easy that is? Right? So from the periodic table, you can write the electron configuration of any element. Okay? Let's have you give it a try. Right? Try to write the electron configuration for bromine, which is right there. The Oh, this is looking so great. Try to type in your answer in the next 10 or 15 seconds or so. Okay, I'm gonna stop it there. The right answer is B, and voila, almost all of you got that. So nice work. How do you get that? You get it because you go backwards, right, to the nearest noble gas, right? So you write that argon core, right? And then you start going to the right from there. You cross the S block with n equal 4, 4s2, 4s2. And then a few of you got messed up on this. When you cross the D block, it's the row number minus 1, right? So it's 3D 10 as you go all the way across. And then you go back to the P block, and the P block is back to the row number again, right? So it's 4P. And then you got to count over 4P1, 4P2, 4p3, 4p4, 4p5, right? So it's 4p5. All right. Awesome. Okay. Any questions? It could be called an abbreviated electron configuration, but it's just more like using the core notation. Okay. So I would say this is using the core notation where you could write out that whole entire electron configuration for argon as well, and that would mean essentially the same thing. All right. Okay. Now, there are a couple of exceptions that I want you to be aware of. All right. And the ones that I want you to be aware of are the ones that occur at D4 and D9 configurations. All right, D4 and D9. And here's what happens. And this is Abe, this was your question from earlier. If you look at chromium and molybdenum, right, you might expect them to be, so you might expect chromium to be argon core, right, 4s2, 3d4, all right? But in fact, that's not the case, all right? Chromium ends up being argon, 4s1, 3d5, all right? Why is that? Well, it turns out there's a sort of a special stability associated with having the d orbitals half filled like this, all right? And we already knew that the 4s and the 3d energy levels are close to each other anyway. Remember this? Remember we went 3s, 3p, 4s, and 3d, and see how they're pretty close to each other. The 4s sneaks in there at a lower energy than the 3d, but they're pretty close, all right? And because they're pretty close, there's some anomalies that happen, and this is one of them, okay? When you get to this place where the d orbitals are almost half filled, an electron will move from the s and go into the d to get that half filled electron configuration, okay? Same thing happens for molybdenum, right? 5s1, 4d5, okay? There's other anomalies here, and there's even more anomalies in the F block, but don't worry about those. These are the ones I want you to know, okay? These two, and then these two, because the same thing happens over here. So when we write the electron configuration for copper, right? We initially expect it to be argon core, right? And then 4s2, and then 3d9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, right? But again, that's not what we get. We get argon, 4s1, 3d10, all right? So it's an exception in the way they filled. It's due to two things: the closely spaced energy levels of the 4s and the 3d orbitals, as well as the 5s and the 4d, which have the same relationship, and the stability associated with having a half-filled D shell and a completely filled D shell. Okay, those two things together result in these two anomalies, these two elements and those two elements. Okay? All right. Try this one.
Wait, Tro, I got a quick question.
Yeah.
So what would the electron diagram look like? Would it just have one up, like up arrow?
Yeah, I'll draw them here for you.
All right.
It'd be Okay, it's looking good. 10 more seconds. Please select an answer in the next 10 seconds. Gabby, I'll get to your question in a minute. All right, the correct answer was E. All right, and a lot of you got it, but some of you missed it. So let's look at what you missed. Some of you put what you might expect from molybdenum, right? For molybdenum, you might expect, if you go back, right, krypton core, and then 5s2, 3d4, 4d4. Now remember, whenever you see that 4d4, whenever you're tempted to write that, go, oh, wait a minute, it's almost half filled, okay? And what happens is when it's almost half filled, it fills at the expense of the s, right? So this is not correct. And instead you get krypton, 5s1, 4d5, right? Those 6 electrons distribute themselves that way instead, okay? The other answer that got a few was D. And the problem with D is that the principal quantum numbers are wrong, right? Because molybdenum is the n equal 5 level, right? It's in the 5th row. You get 5s and then 4d. So it should be 5s and 4d, not 4s and 3d. Does that make sense? A couple of questions. Gabby. Gabby, I can't hear you. I'll come back to you. Emily.
Okay, so I'm just a little bit confused. You just drew the orbital what do we call those? A diagram?
These orbital diagrams.
Yeah, so I'm just confused. Why for copper are they all the positive?
What? Oh, sorry. Go ahead. Why are they what?
All the positive pointing up, and then for the what?
Molybdenum?
Yeah, they're up and down.
Okay, so this is
Oh, copper I meant.
chromium.
Yeah, for
and this is copper.
Okay, so for chromium, they're all up, and then for copper, they're
right. So remember, when you put electrons in, you put them in singly first before pairing them.
Uh-huh.
So the way these would fill would be you'd fill this one, this one, this one, this one, this one, and then if you had another electron, you'd put it here and you'd pair them. So this has 5 electrons, so they all go singly into the 5d orbitals.
Right.
This has 10, so you put 2 in each orbital with their
okay.
paired.
Got it. Thank you for
sense?
clarifying. Yes, I understand now.
Gabby, did you want to try again? Oh, Gabby, I still can't hear you. Sorry, Gabby, if you want to type your question into the chat, then I'll address it that way. Okay, any other questions? Nayeli.
So when you're filling the orbital diagram, you're always going from left to right.
Correct.
Kind of filling the diagram first with the arrows pointing up and then eventually pairing them.
Correct. Yep. Yep, that's right. All right. Let's move. Let's keep moving here. Our next thing we want to look at is how these electron configurations then affect properties, right? How this structure, this is the structure, this is where the electrons are, right? How does that affect the properties of the element? All right. That's where we want to go next. And again, the key is to realize the valence electrons, right? The valence electrons are those highest energy electrons, the ones most loosely held by the atom, and therefore the ones that most contribute to that atom's properties, okay? So the first thing to understand is that when we look at the periodic table, the noble gases have this configuration where the principal level energy levels are full. All right. Notice that if we look down as we look down the noble gases, right? Helium, what's the principal energy level? N = 1. How many electrons does it have? 2. It's full. Neon, Principal level is N equal 2. How many electrons in N equal 2? 8. It's full. N equal 3 is full here, N equal 4, and so on. Okay? And the key to understanding a lot of these properties are that a full principal quantum level has low, the electrons in those orbitals have low potential energy, right? And what do you know about something that has low potential energy compared to high potential energy, right? If a weight is teetering, you know, on top of 6 feet off the ground, right? What is its stability like compared to a weight that's sitting on the ground that has lower potential energy?
It's unstable.
Right. The one that's higher is unstable, lower is stable. So we associate lower potential energy with stability, right? We associate higher potential energy with instability, all right? So these noble gases, these electrons have low potential energy. What does that mean? If chemical bonding is the transfer or exchange of electrons, and these electrons have low potential energy, are they likely to be exchanged or transferred?
No.
No, they're not, right? So because of that, the noble gases are chemically inert, right? They don't tend to react with much, all right? And it turns out that that stability associated with a full outer principal level governs the behavior of many other elements as well. So for example, if we go to the alkali metals, the group 1A in the periodic table, right? The farthest on the left, here it is. Notice they all have one valence electron, right? These metals are basically one electron away from a noble gas electron configuration, right? They're one electron away from that stable, that special stability that's associated with the full outer quantum principal level, right? So guess what they tend to do in their chemical reactions?
Take an electron.
Yeah, they tend to lose that valence electron, right? They tend to lose that valence electron. Remember, that's a characteristic of a metal, right? They tend to lose electrons. Why? Because they're one electron sort of past this noble gas configuration, which has a particularly low potential energy, all right? The alkaline earth metals are 2 electrons away, so they tend to lose 2 electrons in their chemical reactions, all right? Now, if we go to the other side of the periodic table, notice you have fluorine and chlorine and so on. They have 7 valence electrons, right? They're 1 electron short of that noble gas electron configuration, right? So what do they tend to do? They tend to gain an electron, right? They tend to gain an electron in their chemical reactions, right? Because gaining an electron will give them that stable electron configuration. All right, so now we understand a whole lot more chemical, a lot of reasons why these elements over here are metals. Remember the characteristic of metals, losing electrons. And these elements over here are non-metals. Remember their characteristics. They tend to gain electrons, right? Because these elements over here are a little bit past a noble gas configuration, right? So it's easier for them to lose an electron or 2, right, to get there. These elements over here are a little are close to an electron configuration. They can get to that by adding electrons, right? So these elements tend to lose electrons. These elements tend to gain them, and these elements are sort of somewhere in the middle, right? So these are our metals. These are our non-metals. Okay. We can now understand why elements form the charges they do. Remember when we were earlier in this class, we saw this chart that showed us the elements that form ions with predictable charges, right? And they were these, and now we can see why, right? Sodium is +1. Why? Because it has 1 valence electron. It's 1 electron away from this electron configuration of a noble gas, and so it loses that electron to form it. So that's why it forms +1 ions. Magnesium, 2+ ions, because it has these 2 valence electrons, right? And it can lose those. On the other side, chlorine tends to form an ion with -1. Why? Because it's 1 electron away, so it can gain an electron and get the electron configuration of argon, right? Similarly, these guys need to gain 2 electrons, and nitrogen needs to gain 3, right? So these predictable charges that we learned about earlier that we didn't really know why, now we know why, right? The quantum mechanical model tells us, right? And we haven't really done calculations, but you can calculate the energies of these, and you can find that, in fact, the electrons in these elements have particularly low energy, right? And that makes them stable, all right? All right, quick question. Oh, I gave it away, didn't I?
I didn't see it.
Okay. Ten more seconds. Choose an answer. And stop. All right. The right answer was B. So most of you got that. A few of you put A, and a few of you put C. So remember, aluminum is defined by the number of protons. Once you add, you can't add and lose protons. All right, that's nuclear chemistry, a whole nother thing, right? In chemical reactions, electrons are the things that are transferred, all right, but not protons. Here's the electron configuration for aluminum right here. And you can see it's a neon core 3s2, 3p1. So here are the valence electrons. It's easiest for it to lose those 3 valence electrons, right? And then it gets a neon electron configuration. And so if it loses 3 electrons, it has a charge of 3+. Okay, so that's how that works. Okay, very good. Next time, we'll start looking at some periodic trends, specifically atomic size. We want to know how atomic size varies periodically in the periodic table, and then we'll look at a couple other periodic trends, and then we'll finish up the rest of this chapter, and we'll have enough time to review for the exam, okay? And that'll all happen a week from today, right? Because on Monday, that'll happen on Monday. That'll happen on Monday. We'll do that. And then we have a day off the following Wednesday. And then the exam is the following Monday. Yeah? Everybody good? Questions, comments, curses? Everyone survived the election? What a night. Wow. Crazy. Crazy, crazy, crazy. All right. Okay, I think
too many polls.
Jeez, yeah, no kidding. I shouldn't have done any polls today, just because of the error in the polling in the election. That was insane. I've never seen anything. Well, I can't say I've never seen anything like that. It seems like deja vu from 4 years ago. But 4 years ago, I was living in Madrid, Spain, for a year, and I was watching the the election results on the TV, and it was like, of course, it was Spain is 9 hours ahead of us, right? So I was watching it like at 3 in the morning and 4 in the morning, 5 in the morning. I just ended up staying up all night. I was like in complete shock. Anyway, okay. I think we'll stop there.